Today we will start. I will start with the synchronous counters. Okay. Synchronous counters means have you that difference between synchronous and asynchronous counters. We discussed, Common clock is given to all the flip flops, we already seen in the digital. Okay. Just I will show that you will get one idea. Mm, let's see. So common clock is given to all the flip-flops. That is synchronous counter. Okay. So the synchronous counters we already seen. We designed the synchronous counter, 3-bit up counter, and 3-bit down counter, random pattern sequence counter, and next up-down counter. We already discussed it, no? Yeah. So yeah. So suppose if it is a 3-bit up counter. So if it is 3-bit up counter, just I will open this 3-bit up counter. Mm, yeah, this is synchronous counter. Synchronous counter. Uh, yeah, this is up counter. Okay, this is the code for up counter. Synchronous up counter. Okay, so if you see the synchronous up counter, so module synchronous up counter input I am declaring with clock input reset, output reg 2 down to 0 count. So this is 3-bit now. I am declaring with a vector. That is 3-bit. Okay. So declaring with the vector 2 down to 0. Always at the rate passage of clock or negate of reset. Okay. So what type of reset? This is a synchronous reset or asynchronous reset? This is asynchronous reset. Okay. If it is synchronous reset, it means you have only passage of clock only. So yeah, we have a discussion on this when I explained the D flip flop. Okay. So passage of clock or negate of reset begin if not of reset. That means if reset equal to 0, count is initialized to 0. Okay. Else count equal to count plus one tick binary 1 and end module. Is this code is fine? Okay. And coming to the test bench. So test bench for sequential circuits, you have 5 steps. First, you need to so module, my test bench module name, and you need to declare the internal variable. Clock and reset with reg data type and count 2 down to 0 count with write data type. You need to instantiate your design in the test bench. Okay, so that means design name followed by instance name, and this is what connection by name. Okay, and next clock generation. Okay, so clock generation you can use always or you can use forever also. So when you are using forever means you need to use initial and initial begin. Okay, you need to write between the initial begin clock equal to 0, initialize the clock, forever #5 clock equal to not of clock and end. Okay, this is clock generation. Okay, and next I am giving the stimulus initial begin. First I am applying the reset. So this is active low reset now. So first I am applying the reset equal to what 0, and after 10 time minutes I am releasing the reset equal to 1, and I'm checking for 8 clock cycles whether it is it is performing the up counter or not, and again you apply the reset. This is the end of the simulation dollar finish. So if you want to see the outputs in the TCL console, I need to use the initial begin dollar monitor, time equal to percentage d, reset equal to percentage b, count equal to percentage d, comma, dollar time, comma, reset, comma, count. Okay. So this is the test bench. Is it fine? Okay. Yeah, this is up counter. I think you can see in the Vivado, no? Uh-huh. Okay. Mm. Mm-hmm. SISO PISO also. Okay. Okay. It's there means you just you see in that tool itself. Okay. You tried. Okay. Okay. Yeah. Yeah. Simulation you tried. Okay. Okay. I will show just yeah, coding part. So this is down counter. Count equal to what? Count minus one tick binary 1. Same thing. So you need to declare a synchronous down counter, clock reset, output range 2 down to 0. It's always positive. Yeah, means in the D flip flop, I told you, no, there are two types of resets are there, synchronous reset and asynchronous reset. Okay. So synchronous and asynchronous reset. Suppose if you take the synchronous reset, when it is going from reset mode to functional mode and functional mode to reset mode, both are depending on the clock. Okay, both are depending on the clock. So both are synchronous with the clock. Okay, whereas the passage of clock or negate of this is asynchronous reset. So asynchronous reset, if you take when it is going from reset mode to functional mode, that is synchronous with the clock, and when it is going from functional mode to reset mode, that is independent of clock or asynchronous with the clock. Okay. So when you are when you are using synchronous reset, sometimes your design means your design clock will not work. If you try to reset your design, so you can't reset your design now. So that's why so mostly in the industry we are using asynchronous reset. That too asynchronous active low reset only. Why? Because that power I told you, no, you are when it is active high means what? You are operating your reset when the power is on. Okay, you are operating in the functional mode when the power is off. Okay, so that is not recommended. So in the VLSI we need to we need to operate your reset when the power is off. Suppose your mobile is there. When mobile is switched off, all the peripherals present in the mobile will get reset, no, when the power is off. Okay. So when the power is on only, all the ICs, so whatever the ICs are there, that should go into the functional mode. Okay. So this is a down counter and test bench is same only. And random pattern sequence counter. So just this is random pattern sequence counter. So we already seen the random pattern sequence counter. This is random pattern sequence counter. So it should count from 0, 1, 3, 4, 5, 7, 0. No, like this it should count. So here I developed the random pattern sequence counter. So module random underscore counter, input clock, input reset, output to reg 2 down to 0, Q, okay, always at the rate passage of clock or negate of reset, begin. If not of reset, so Q is initialized to, it will start from the state and else begin. I am using case statement, okay, I am using case statement. So if it is 0, what is the next state? 1. If it is 1, it will be 3. If it is 3, 4, 4, 5. 5, 7, 0. Okay. So for case statement, I told you, no. So there will be a default. Yeah, it will be like initial state. Okay. So test bench is same only. So you need to initialize the reg variables and instantiate your design in the test bench, generate the clock, and initialize the reg variables. And after so apply the reset after 15 time units, release the reset. I need to check for 120 nanoseconds and dollar finish. I need to see in the outputs in the TCL console dollar monitor. Okay, this is the test bench. Is it fine? Random pattern sequence counter. Okay. Next, mod 6 counter also you can design. Okay. So this is mod 6 counter. So what is mod 6 counter? Same thing. If reset count equal to 0 and else if so it should count from where 0 to 5. When it is coming to 5, it will reset to 0. No, okay. So I am checking for the condition that if count equal to 5, count will be initialized to 0. Else it should do normal count. Okay. Okay, this is mod 6 counter. And next, decade counter. Decade counter means what? It we should count from where to where? 0 to 9, no? Mod 10 counter. Decade counter same as mod 10 counter. 0 to 9. So you are using 4 bits, no? So 4 bits, 4 flip-flops you are using. Okay. So decade counter we already discussed in digital, no? Decade counter. Okay. So always at the rate passage of clock, negate of reset. If not of reset, I am initializing the counter to 0. Else begin, I am checking for this one condition. When it is 9, so count will roll over to 0. Otherwise, count normally it should count. Okay. This is the decade counter. And next, mod 13 counter also. It should count from where to where? 0, 0 to 12. So I am checking for the condition. So that means if we count equal to 4 tick D12, it will roll over to 0. Otherwise, count equal to count plus 1. Okay. So this is the mod 13 counter. And up down or up down counter. Up down counter means we already seen the up down counter, no? This is up down counter. Okay. So up down counter. So here I am writing the code for the up down counter. So here, so here edge clock or edge reset. I am declaring one control. Here one control is there now. That is M. When M equal to 0, it will do up count. When M equal to 1, yeah. So this is up down, up underscore down. I am initializing. One second. Here this is test bench. This is count. Yeah. This is my design RTL code. So I am declaring. So up underscore down is 1 means it will do up count. 0 means down count. Okay. So always at the rate passage of clock begin. If reset, count will be initialized to 0. Else begin. If up count will be incremented. Else count will be decremented. Okay. So this is up down counter. Okay. So these are about synchronous counters. All counters we covered now. Yeah. So next is shift registers. Shall we go or you will practice this and you will come back? Shift so PISO, okay, SISO, PISO, all you universal shift register. Universal shift registers. If you see universal shift register, so here if you see, so module universal shift register input clock reset underscore n. I am selecting, so I mean selecting one input that is 2-bit select operation, 1 down to 0 select operation, that is 2-bit, and input 3 down to 0, this is parallel in data, and input yes serial left D in, this is serial left data in, input serial right data in, and output reg, this is 4-bit, 3 down to 0 P out, parallel data out, and output serial left data out, and output serial right data out. Okay. So always at the rate passage of clock begin if not of reset. If reset equal to 0, I am initializing parallel out to 0. Else begin, I am using k select. Okay. So what operation it will do? Right shift, left shift, parallel in parallel out, or yeah. So if it is 1 means what? So that logic you know, no? So when it is uh, this logic you know, no? You are using concatenation operation. That means shifting s underscore right underscore d in will be coming, and every time this copy will be coming. That is p underscore is coming 3 into down to 0. If it is right shift, okay. If it is left shift means so every time this p underscore d out 2 down to 0 is copying, and so s underscore left shift is coming over here. So we are combining with a what operator? This one concatenation operator. Concatenation operator. Parallel in, parallel out means what? 4 bit of data, whatever the 4 bit of data is there, that is given to the P underscore D out. And default is do nothing. Okay. End case, end, and end at last. So for serial, where you will get the data? Serial left D out. At P D out, 0, you will get the data. And right D out, you will get at P D out 3, you got the data. So this is universal shift register. Is it fine? Okay. This is universal shift register. And special counters also we discussed, no? Ring counter and Johnson counter. This one you did shift register. This is ring counter. So what is ring counter? Like we are giving Q as a feedback to D, no? So what is the initial state? Q naught, Q1, Q2, and Q3. That is 100 is my initial state of the ring counter. And it will every time it will be shifted. It will be shifted feedback. Okay. So ring counter also I wrote the code. So this is my code. So these are the special counters. So module ring underscore counter, input clock, input reset, output reg. How many bits? How many flip flops we are using? 4 flip flops now. So 3 down to 0 Q. Okay. So 3 down to 0 Q. Always at the rate passage of clock or passage of reset. Begin. If reset. Okay. So what is the initial state? Q naught is 1 now. Others are 0. So that means Q naught is the LSB. So that is initial state is what? So Q is non-blocking with photic binary 0 0. Okay. Else begin. So I need to do shift operation. That is what is shift operation? Q2 down to 0 comma Q3. Every time the Q3 should come now. Shift operation. This logic is shift operation only. Is it fine? Ring counter. Okay. And mm, mm, like that it is coming. Yes. Okay. Every time it is copying. Okay. Q of 2 down to 0 is copying. And Q of 3 is coming back like this. Okay. This is ring counter. And next is Johnson counter. Johnson counter, what is the change? This complement of last flip flop is acting as a clock for giving the feedback, no? Input, yeah. Input, we are giving the feedback, okay? So it is act as mod 6 counter also, we discussed in the digital, okay? So, okay. If you see the Johnson counter, this is the Johnson counter, yeah. This is the Johnson counter. So input clock, input reset, output reg T down to 0 Q. Always is there a passage of clock or passage of reset. Begin if reset. Okay. I'm initializing. Okay. And else begin. Feedback logic I need to develop. What is the feedback logic? Q not equal to what? Not of Q2, no? Okay, not of Q2. Q1 equal to Q naught, Q2 equal to Q1. This is the feedback logic I need to develop for the Johnson counter. Is it fine? Okay, this is the Johnson counter. Okay. So with this, we completed uh, counters and shift registers. Next, we left with frequency dividers. Frequency dividers. We left with frequency dividers. Next, sequence detector using FSM, serial adder, RAM design, and synchronous FIFO. Synchronous FIFO, I will tell you. And one small topic, functions and concept, functions and tasks are there. And if time permits, we'll do one project related to I2C. Okay, I2C will develop and will write the Verilog code, RTL code for I2C that you can keep as a project for RTL. Okay. Tomorrow we'll see frequency dividers, and if time permits, we'll start with sequence detectors also. Okay.